Good morning, guys. So apparently, Schoology's on strike today, and Zoom is on strike today, and everything else. So here is our notes, and we'll talk through what we learned in class today. And then maybe this will be helpful if you're in first hour and you need some extra. So of course, our very first, most important, is our attendance question of the day. You need to get rid of one: waffles, French toast, pancakes, or donuts. What must go? But in all seriousness, take a minute and pause the video right here. Well, apparently my pen won't work. There we go. Pause the video and let's try this warm up. And then we want to find the perimeter bounded by y equals x squared. Y equals the square root of 18 minus x and the x-axis. Okay, so you guys remember, perimeter is really just an arc length issue, right? So perimeter is the total of all of our arc lengths. Well, if I could spell today. Perimeter equals the total of all arc lengths. And of course, we definitely didn't forget our formula for arc length, which is the integral from a to b of the square root of 1 plus our derivative squared. Honestly, you guys are in a good situation with it being remote because you get to have your notes all the time. Less memorization of formulas. So here's the one I'm going to call this first one f of x, which is x squared, which makes f prime of x be 2x. G of x is this guy over here, right? G of x is the square root of 18 minus x, which is really 18 minus x to the 1/2 power, making g prime of x to be 1/2 times 18 minus x to the negative 1/2 times negative 1. It totally says negative 1 over there, giving us negative 1 over 2 times the square root of 18 minus x for g prime. So our arc length, or our perimeter is going to be the integral from 0 to, oh, of course, I made this nice point of intersection of 2 4. So from 0 to 2, we integrate that red line, so the square root of 1 plus 2x squared dx. And then we will add the blue line, so the integral from x equals 2 to 18, also carefully chosen. The square root of 1 plus, and then we have negative 1 over 2 square root of 18 minus x squared dx. And then we can't forget the piece that we all like to forget, which is this line right over here, right? Now, we may have to use Pythagorean theorem, but it's not an angled line, it's a horizontal line, so we know that distance. It's just right minus left. So we do need to add 18. Now, when I put this into my calculator had to definitely think for a minute. It was not the fastest integral that my calculator has ever done. Also, you don't really want to do this integral by hand. You get some disastrous stuff that we don't know how to integrate. So I got my total perimeter to be 39.465. So a little review on arc length and perimeter that's coming up on our test. Remember, our test is a week from today. All right, things I wanted to make sure that we mentioned. Do you need a retake from chapter 5? If you do, what questions do you need to retake? And do you need more practice or help before you do the retake? So if you haven't already, email me and tell me what questions and if you need help. Do you need help? And hopefully by then Zoom won't be on strike and we can set up like a Zoom meeting or something. Let me know if you guys have any questions. Hopefully you guys can get some extra sleep this weekend. And yeah. Have a good Halloween. Okay, so yesterday we were talking about centroids and moments and mass and all of that. So the first thing I wanted to talk about was just a little bit about total mass. Okay. So this, we have a linear mass density. A linear mass density means this is the mass per centimeter. So I have like this little thin rod, okay, and it runs along my x-axis, and it's physics, so it can be like infinitesimally thin or whatever. But what they're saying is the linear density is 9 grams per centimeter. So that means if I have 1 centimeter, then I know that that weighs 9 grams. Now this is a constant density, right? Each one of these is going to have the same density. So if the rod is a total of 10 centimeters long, our total mass is just our density, our linear density, times our length, which is really just 9 grams per centimeter times 10 centimeters, and we get a mass of 90 grams. Okay? Easy peasy. Just the idea behind it of what we are getting our total mass by getting the density, finding the density times the length, right? So this one is a little bit trickier because this time the density they gave us is not constant, right? So this time, if I have a 2-meter rod, I can't just be like, this is the density here and this is the density here, and they're both 9, so I have a total of 18, right? Obviously, those numbers are just all fake, but the idea is our density is changing. So density is changing. So if our density is changing, we can't just take the whole thing, but we can take a little tiny slice of it, right? And we can say, oh, well, this has a width of dx and our length of dx, and its density is rho, whatever rho is at the moment in time. So the mass of this little piece right here, where I put my integral in, the mass of this little piece right here is p of x dx. But I don't just want this little piece right here. I want all the pieces from here to here. So I must need to accumulate them or integrate them from 0 to 2. 1, whoops, I can write 1 plus x, 2 minus x, dx. So what the whole point of these problems are, and the whole reason why I had us do these problems, is I wanted to introduce this idea of if we take our density and we multiply it by like a length, if it's a linear density, or whatever sort of, it'll depend on our units, but our density times something can give us our mass. That's where I'm going. Density times some either length or whatever, area, length, etc., equals our mass. This integral, by the way, comes out to 3.22. And that would be kilograms, right? Because it was kilograms per meter times meters. Okay, so let's leave one dimension, but we are going to go back to a constant density. So we're going to leave this idea of our density is changing. We are going to go back to a constant density, but we are going to move away from this linear situation into a two-dimensional situation. So I have a two-dimensional object of uniform density. So say I have like this rectangle, okay? Uniform density means that there's not parts of my rectangle that are like heavier or thicker than other parts, so I don't have to worry about any sort of imbalances there, right? Uniform density, it's going to be kind of uniformly balanced. So what we know is we can find our moment. So our moment would be, well, our moment would be like, say I Oh, I wanted a different color. Say I put my x-axis right here. And I put my y-axis right here so that my rectangle is nice in the corner there. I could find the total mass if I had, see, our density is equal to, well, I guess our density is going to be given to us in a mass per area units. So if we want our total mass, we would take our density times our area would equal our total mass. Like I wanted the total weight of the, not weight, but mass of this, okay? And the reason why we care about the total mass is because what we were talking about yesterday was our centroid is located at our moment about y over our total mass. So that's the x coordinate, and the y coordinate is our moment about x over the total mass. And so our moment, we're going to get there in just a second, but let's just think about where our centroid would be. You guys know that if I need to find the balance point, if I have this nice uniform rectangle, is going to be in the middle. So if I call this side L, we're at 0 here. And if I call this side H, we're at 0H here. We're at LH in the corner. And then the centroid, the X bar, Y bar, the balance point of this is just going to be in the middle, right? Half of L and half of height. Halfway over and halfway up. That'll be our centroid. Okay? So, if we think about those moments, then, oh, I'm getting ahead of myself. I'm getting all excited. So I guess where I wanted to only talk about with this slide was I wanted to talk about if we take our density times our area, that would give us our total mass, okay? And the reason why we care so much about our mass is, remember that mass times our distance gives us that moment. So where we're going here in a second is we're going to start letting things move a whole lot more and getting into our integrals. And so we're going to need to be thinking about, like mass, distance to get moment, and also mass, right? So if our total mass is rho times area, then rho times our tiny area would give us our mass at any moment in time. All these moments everywhere. Hear me out. Let's go and look at this next one. Okay, so a planar lamina. I assume you guys have never heard of it because, well, I don't know. I hadn't heard of it before I got to this point in math. So a planar lamina is just a really fancy word for, I have some in here. I have some other, my functions always come out way too similar. We're going to go from A to B. Okay, so what's going on? I don't want crayons. What's going on is we have some sort of area, usually trapped between two curves. And we want to find maybe the centroid of this weirdly shaped area. Okay? And so it's not nice and rectangular anymore. But we know from calculus that if we zoom in enough, we can make anything look nice and straight. And we can get little tiny rectangles from anywhere. So for each one of these rectangles, I could find its mass, right? And I could find its moment. Mass being density times area, and moment being mass times distance. Which means the moment we're going to have to use rho times area to get our mass times our distance. That all follows. So what we want to think about is, first of all, our total mass, just because it's a little bit easier. Because we said mass was rho times our area. Now, rho, like I mentioned, is for our density. But the really thing that I want you to know the really other important thing about rho for us is rho is constant. So to get my total mass, you guys know how to find the area of the highlighted. It's just the integral from a to b of f of x minus g of x dx, right? I multiply that by rho and I get my total mass. So now what I'm going to go into is I'm going to go to the next slide and I'm going to make another picture. And what we're going to do is we're going to start thinking about what is the moment of each of these rectangles so that we can get our total moment, right? Because when we were doing this yesterday, we were just dealing with little point distances, right? So we would find this little guy's moment, this little guy's moment, right? And combine all of them. So we're going to take that same approach, but they're all close to each other, and we're going to find the moment of like each little dx rectangle. Okay. So remember what we established right here was that our total mass of our planar lamina is rho times the area. And finding the area between two curves is not anything new for you guys. Okay. So now I wanted to move to our moment about y. So the moment about y, I said yesterday how likely, and I'm not sure that maybe likely is the best word for it, but it's sort of the tendency to spin. It's a measurement of how much we kind of want to spin. I realize that my f and g are different. It's okay. Don't worry too much about it. They just are arbitrary calculus curves anyhow. And then we're going to go from A to B. So our moment, and if you do a better job and draw your pictures more closely, that's good too. I just couldn't remember. Slightly different looking picture. So let's go to our moment about y. Thinking about our little dx rectangle, we know that moment is mass times distance. Okay. So, and we want to take the distance from, well, if it's the moment about y, that is where x equals 0. So that's from the y-axis. So here's our y-axis. This horizontal distance over to my rectangle at any given moment in time is x. So the mass, well, I know the mass. The mass is the area times rho. The area of this little rectangle is height, f of x minus g of x, times width, which is d of x. So our moment about y, or our measurement for the kind of tendency to spin around y, is the integral from a to b of our mass, so rho times f of x minus g of x, times our distance, which is x. I'm going to rewrite that just a little bit. Maybe I'm going to write it just a little bit. The moment about y is rho. I'm going to move rho outside because it's going to be constant for us. A times b. I'm going to put the x first. X, and then remember we're using the area. Oops, it's supposed to be a g. G of x dx. Okay. So this is distance. This is area, because area times rho gives us mass. So now that we have our moment about y, the reason why that's important is because then we can use that to find our x bar, but we'll get to that in just a second. Let's talk about the moment about x first. So same thing, this is like we're gonna spin around our x-axis. So we know it's gonna be a mass times a distance again. Let's think about what exactly that means in this situation. So here's our f of x. And then we'll draw in our g of x maybe. Or maybe I'll just fight with smartboard forever. And then of course, we're still going from A to B. And here's our little area between two curves. And here's our little rectangle. Here's our little rectangle. Okay. Now this time our distance has to be from the x-axis, which is from where y equals 0. So these are going to be y distances, right? The problem is here, first we think we should go to the bottom of the rectangle, but that's not really right. And then we think maybe the top of the rectangle, but that's also not right. Where we want to go is the center of the rectangle, because we are trying to find our centroid after all. So it'll be the middle of that rectangle. The middle of the rectangle before was irrelevant because it was so infinitesimally small. So the middle of that rectangle. The middle of that rectangle is the value that's right in the middle of the value of f of x and g of x. So if I need a number that's right in between two other numbers, I need to average it. So the middle of that rectangle is the average. So that is f of x plus g of x over 2. The rest of this is the same because the rest of it was our mass, and our mass is not changing. So the mass, we're still going to use that area times rho times area. Which leads us to our moment about x being the integral from a to b. Mass is rho times the, well, you don't need to write another integral sign, that one's excessive. Rho times the area, so f of x minus g of x. To turn it into a moment, I need to multiply by the distance, which is f of x plus g of x, because it's that middle of that rectangle, dx. I'll rewrite it, mostly so I can move the row out. The moment about x, a to b of rho. I like to leave it in here, f of x minus g of x times f of x plus g of x over 2. I have seen places where they simplify it, but for me, if they simplify it, then I feel like I lose that idea of the area and the distance, and that really helps me when I'm sorting out how to do these problems. All right, I think I have one more slide where I want to kind of clean this all up and write it all down. Yes. So the center of mass of a planar lemma. Our mass, remember we said is rho times area, which means it's rho times the integral from a to b of f of x minus g of x dx. We should probably draw a picture here because, oops, I don't even know what I pushed there. Because if we don't have a picture, then it's not really obvious that f of x is on top. And all of our equations that we have written have assumed that f of x is our top function. Otherwise, we would get potentially negative values. Here is the area we're looking at. Okay. Oh, and then I know what I wanted to write. I wanted to write one more thing. I wanted to write that rho is density of our planar lamina. Okay, so that's our total mass, right? The other things that I wanted to write down were our moment about y, which we said was rho times the integral from a to b of our area, f of x minus g of x, times our distance, x dx. I wanted to write down our moment about x, which is rho a to b, our area, f of x minus g of x, times our distance, which is f of x plus g of x over 2 dx. And then the last thing I wanted to write down was I wanted to write down our centroid. So our centroid, or our center of mass, which really is in the same place as our center of gravity as well, is x bar, y bar, okay? Now what's important is that you guys recognize that x bar is our moment about y divided by our total mass. And y bar is our moment about x, because those are using y distances, divided by our total mass. Which means that x bar is rho times the integral from a to b of x times f of x minus g of x dx, all over rho a to b of f of x minus g of x dx. Now, you can cancel the rows, but nothing else cancels. That f of x minus g of x doesn't cancel because of the inside-outside, or because they're both inside the integral. So don't get over-aggressive with your canceling there. Rho a to b, right, let me move this down, actually. So our y bar, the y coordinate of our centroid, is the same thing, rho moment. So our moment for that was area, f of x minus g of x, times distance, f of x plus g of x over 2 dx, over our total mass, which is rho times area. And of course, the rows can cancel, but don't go canceling anything else. All right, let's look at a couple of examples. Now, I know this sounds intense, but if you like really understanding these makes your life easy. If you don't understand them, then you need to be able to use them. But really, we are going to be using to find different pieces, x bar, y bar primarily. X bar. I believe on our homework it has it do it separately. Find the moment about y, find the mass, find the moment about x, and then find x bar, y bar. Or maybe it doesn't ask you to find the total mass on your homework. It just asks you to find the moment about x and the moment about, the moment about y and the moment about x, and then the x bar, y bar, but you still have to find the total mass to do that. Okay, example. So if you're feeling brave, try it, right? Our second one is right here at y equals 0, because this is the area that we're interested in, right? So we know our f of x, like I said, our g of x is just this bottom line. So if you want, take a second, pause this, and see if you can try this. Whoops. Okay. Now that you're done pausing and trying this, let's look at it. So I want the center of mass. So they're saying find x bar, y bar, okay? X bar is the moment about y over our total mass, okay? And we know total mass is rho, which I for some reason fought with it and couldn't get it to row, so I just left it as P. Row times our area. Our Y bar is our moment about Y over our total mass. Okay. So let's see what that looks like. I like to draw in my little rectangles still because I like to think about them. This distance I realize is X, and this is just F of X. So our total mass is just rho times the area. So that's just rho times the integral from -2 to 2 of 4 minus x squared dx. Oh, maybe I never actually calculated these things. Yeah. Okay. So I got 32 rho over 3 for my total area. Just leave rho as rho. Total mass, I'm sorry. 32 over 3 is my area. 32 over 3 rho is my total mass. Okay, so now if I want to find my moment about y, my moment about y is how likely it is to spin around this line. So that's my mass times my distance, and my mass is just the same as my area times rho. So my moment about y is mass times distance, right? Whoops. I swear I can do this. So my moment about y is rho, is the integral from a to b. To get mass, I need area times rho. So area was f of x. There's no g of x to subtract, minus 0 if you wish. And distance is just x. Yes. It's like f of x minus g of x times x. And then this one, I think we come out with a very exciting value of 0. This should make sense. We're saying that the balance point of this area would be right here somewhere along the y-axis. So like, oh yeah, it's symmetrical. That totally makes sense. So I'm going to leave my moment about y for a minute. Actually, I'm not. I'm going to stay right here and say x bar is my moment about y over my total mass, which is why when I got 0 over that 32 rho over 3, we just got 0 for x bar. Okay. That is unnecessary. Our moment about x is still a mass times a distance, and mass is still rho times area, -2 to 2. Area is still going to be f of x minus 0, right? And then the distance. This time, we want the distance out to the center of mass of my little rectangle. That distance is half of my f of x, right? F of x minus plus 0 over 2. Let's definitely say plus because I want that average of them, dx. So then when we do this integral, I thought I did this integral. Yes, I did. There we go. Let's see if it'll cooperate for me. Somewhere. I got a row 256 rho over 15. But my that's where I was going with this is my total mass is still the same. So my y bar is mx over the total mass, which gives us that 256 rho over 15 over the 32 rho over 3, which is divided by, yes, sounds right. So 256 over 15 times 3 over 32, right? This becomes a 5. This will become a 16 and a 128, and you can continue doing that. So we get y bar is 8 over 5, or that's like 1.6. So it's saying that our centroid, or our center of mass, or our balance point, is at 0, 1.6, or 0, 8/5. So we go back up and look at that, 1.6. It's saying like right about here is where it would balance. Looking at that, I would say that looks pretty reasonable because this side this side up here isn't as thick as the side down here, so it's not going to be as heavy. Cool. Okay, I have one more example that I wrote for you guys. It's not terribly different. It's just this time we actually sort of have a more of a bottom function than 0. So it's just this area between, I used the same f, but I gave us a new sort of function. So, of course, these points where we intersect are important. 1, 3, and -2, 0. The same idea. Start with your total mass. We know is rho times area. So our total mass is just rho integral from -2 to 1. Oh, I guess I should have told you guys to pause it. Of f of x minus g of x. So on this one, when we use our calculators, and of course here I'm putting like f into y1 and g into y2, and then using like y1 minus y2 and things like that to make my life easier. Let's see. Did I do this? I did do this. And I got that it was rho times, whoops, let me erase that. Rho times 4.5, 9 over 2. So I'm just going to put 4.5. Okay. And then we need to set up our moment about y. So rho, -2 to 1. Area is f of x minus g of x. But then, if I'm going off of here, I need that distance x. So our moment about y is a -2.25 rho. So we're saying that our balance point is going to be to the left of this. That seems reasonable to me. Our moment about x, of course, you know, that's the tendency of it to spin here. So this is where we need this distance, right? This middle is going to be f plus g over 2. So same thing, rho, -2 to 1 of my area, f of x minus g of x. This time times my distance, f of x plus g of x over 2, my distance to the middle of that. And then this one, I got 10.8 rho. Now I know that your homework asks for some of these values individually. Then of course to find our centroid, x bar is my over our total mass. And y bar is mx over our total mass. So you guys are seeing how the rows are going to cancel out, right? X bar is, what was that? -2.25 over 4.5, -2.25 rho over 4.5 rho. So I got x bar to be, where did I do that? -1/2. Y bar, of course, is my mx, which was the 10.8 rho over my total mass of 4.5 rho. And so I got that to be 2.4, which means our centroid or our center of mass, or our balance point is at negative 0.5 ketones. All right, hopefully that's enough to help you guys out. So try these homework problems. Let me know if you guys have questions, and I hope you have a great weekend. Thank you.